So I got this whole rig going, so might as well talk about another problem that I wanted to chat about, which is, it was covered in class earlier, and I had another way of explaining the problem that I thought might be useful. So this is the book on shelf problem. I'll call it that. Book on slotted shelf problem. Okay, so what's the problem? The problem is you have a shelf, let's say it has 24 slots. And you want to place books on the shelf such that no two books are directly adjacent. So we can put these books in little slots here, and we don't want the case where two books are right next to each other. So let's say we have, in this case, I think in the problem we had 6 books. If the numbers are not right, then I don't know. I mean, whatever, this works. So in the problem we had 6 books, and we want to count, this is a combinatorics problem, we want to count the number of ways to rearrange these 6 identical looking books on the shelf such that no two books are adjacent. So you're allowed to have a book in the last slot, and you're allowed to have a book in the first slot, just no two books can be right next to each other. So one way I thought of solving it that would actually kind of illustrate some concept is by constructing a bijection. So I'll talk about what a bijection is afterward. So first off, here's the general idea. So in this case, so original. So let's say we have an original assignment. So an assignment in the original case is an assignment of books to locations such that no two of these books are right next to each other. Right? So let's say we have a particular assignment of books. We're going to transform this into a new assignment of books, but it's going to be on a 19 length shelf. So this 19 length shelf is a little bit different. So it allows books to be directly adjacent, and we've constructed this shelf by just getting rid of the slots in front of each of the books in the previous shelf. So the last book here, if it's on the edge, it has no slot to get rid of, so we don't get rid of it. But for all of the other books, we get rid of the slots in front. So actually, just to clarify, even if this book were not on the last slot on the shelf, let's say it were here. The last book, we do not get rid of the slot in front of the last book. So in total, we're getting rid of 5 slots, right? There are 6 books. There is some last book, and we're not getting rid of the slot in front of the last book. So we're getting rid of the slots in front of the remaining books. So this is why the length of this is 19, and the length of this is 24, because we're getting rid of 5 slots. So first off, can we always do this? Can we always get rid of 5 slots? Yes. Well, since every book, since no two books are adjacent, the first 5 books can't have another book in front. If they did have another book in front, if they had another book in the slot that we're going to remove, then there would be a contradiction. This wouldn't be allowed, right? So we can always do this. We can always construct a 19th length slotted shelf in this way, right? So we have a way of taking this, transforming it to this case. And so now we have this case. So we have books on a shelf, and we have no constraints. We just have books on a shelf. So how do we count the number of ways of rearranging the books on the shelf where there are no constraints? The number of ways of doing that is 19 choose 6. So this is, you can think of these as bits. So a book, if the slot is filled with a book, then that's a 1. And if the slot is not filled with a book, that's a 0. So we can think of this as 0, 1, 1, 1, 0, all the way up to, this is length 19. And 6 of these are filled because there are 6 books in these slots. And so 19 choose 6 is the number of ways of commuting this bit vector. Okay, so that allows us, so we have this way, and we have this way of counting here. So how do we prove that this is the number of ways of commuting the books in the original case? So the way we prove that is by constructing a bijection. So what is a bijection? We have two sets. A bijection is a one-to-one onto mapping, right? That's formally. But basically, it's a mapping of each point to exactly one other point in the other set. So the one-to-one part means no two of these can map to the same one, and the onto part means every point here is accounted for. And because it's a function, every point here is accounted for. So intuitively, it's just a matching of these points, such that every point here is covered, every point here is covered, and they're exactly matched. That's what a bijection is. So to prove this is a bijection, we just need to prove that we have a function f that maps from set cases here to cases here, and an inverse function that maps from the range of f, all the cases that are mapped to here, back to examples, such that f of f inverse of x is an example from here, is equal to x, right? So if we transform the books, so I'm going to argue this intuitively, and I think it's close to formal. So if we take books here, take these books, we want to show that if we map them here and back, that we've reconstructed the original case, right? F of f inverse of x is x. And if we've done that, then we've proven that f is a bijection. And we're done. I'll say why we're done after. So how do we show this? So take this case here. We get rid of the slots. How do we map back? Well, take the first 5 books, put slots in front of them again, right? Not the last book. Just take the first 5 books, put slots in front of them, and then that transforms you back to this case. So first off, if we put 5 slots in front, the length of the number of slots is now back to 24. So we're good. If we put 5 slots in front of the first 5 books, then you cannot have 2 books that are adjacent, right? So the last book, you don't need a slot in front because there's no, you can think of it, if you're adding a slot in front, so let's say you had this originally. In this case, the 1926, you had 2 books that are adjacent. In the mapped case, you would have a book, a slot that was created, and then another book, right? And you don't care about mapping, you don't care about adding a slot in front of the last book because there could not possibly be a book in front of the last book. So this addition of a slot is not necessary to ensure that no 2 books are adjacent. So you can say that after you map back, after you've added these slots back, there are no 2 books that are adjacent. And that's it. So that's intuitively, I guess, why it's a bijection. And so once you have a bijection, once you have like a pairing of these, you can say that, so if there's a bijection between 2 sets, so f is a bijection that maps, let's call this the original to, I don't know, this is the final, right? This is a set of these cases, and this is a set of these cases. If f is a bijection, then the sizes of the sets are equal. So this tells you that since we know the size of this set, there are no constraints on this, right? And we've computed it. And we've shown that f is a bijection that maps this set to this set. It doesn't matter, you can get an inverse and it's also a bijection. Then we get this result, which tells us that S sub O equals 1926. Since this is equal to 1926, right? That's it, we're done.